Hi everyone. So in this video we will look at matrix formulation and solution to the problem on page number 32 and 33. So just as a refresher, in matrix world we write down y as x beta plus error term. Y is a matrix as x beta epsilon. Everything is here is written in terms of matrix, right? So if we are dealing with simple linear regression, the beta hat is equal to x transpose x inverse x transpose y, and y hat is equal to x beta hat, or x times x transpose x inverse x transpose y, where this thing is called hat matrix because it is putting a hat on y, or basically estimating y's. So this is called hat matrix. Variance of beta hat is just variance of this thing, or is expected value of beta hat minus beta hat minus beta transpose, and if you simplify it, you're gonna get x transpose x inverse sigma square. This thing that you see here, let me use a different color. Is the variance covariance matrix, also known as variance covariance matrix, in the simple linear regression world, because this is going to be equal to, so this x transpose x inverse in simple linear regression world, where our design matrix is just a 2-column matrix. So your y would be something like this: y1, y2, yn, right, is equal to x, which is 1, x1, 1, x2, 1, xn, times beta naught, beta 1. Later you can just expand these results. All you're going to do is make the dimensions of these matrices bigger. When you, instead of simple linear regression, you have multiple, so it will have more columns. Right, so in simple linear regression, x transpose x inverse is representing, it will represent variance covariance matrix everywhere, but this x transpose x inverse in simple linear regression simplifies to sum xi over n sxx minus x bar over sxx minus x bar over sxx 1 over sxx. And these diagonal elements that you see here, these are the variance of beta naught and variance of beta 1. If you recall, variance of beta 1 hat from your linear world, it was sigma square over sxx. So the sigma square is right here, and then this. So these are the diagonals, are the coefficients of the variance of beta naught. So this is the coefficient of variance of, from here you can see variance of beta naught hat is equal to sigma square sum x, sigma square over n sum xi over sxx, and this is sigma square over sxx. One thing that you will have to do, these things that you see here, okay, so I don't have this and this, they are same because they both represent covariance of beta naught hat and beta 1 hat. So this represents covariance of beta naught hat and beta 1 hat. So we are going to calculate all these things. One additional thing that we need to do is to figure out this nuisance parameter, sigma, the estimate for sigma square. And the estimate for sigma square, sigma hat square, is SSE divided by n minus 2, and which is equal to y transpose y minus beta hat times, I want to write it bigger, sorry, so I'm gonna just erase all of it and rewrite it. So sigma hat square is equal to S square, which is SSE over n minus 2, which is in matrix world it is y transpose y minus beta hat x transpose y. So some of the things, these things are like you need to remember all these formula, or not remember but at least put them on a chart so that you can refer to them. So this is all we need to solve the problem on page number 32 and 33. So let's get to that. So in the last video you saw we fitted a regression, we found the least square estimates using matrix algebra. We're going to do the same, but this time it's going to be a little bit bigger matrix because we are going to fit the same data that we were working on, y and x values 0 0 1 1 3, and x values are -2 -1 0 1 2. Same data, but the model that we want to fit this time is y equal to beta naught plus beta 1x 1 plus beta 2 x2 square plus some error term. So we want to include another item here in our list. So we're going to have that as x squared, which is square of -2 4 1 0, square of 1 is 1, square of 2 is 4. So if I write down my design matrix x, it's going to be 1 1 1 1 1 -2 -1 0 1 2, and then I have it square, so 4 1 0 1 4. X transpose x, so we're going to calculate all the stuff that we calculated last time. So it's 1 1 1 1 1 -2 -1 0 1 2 4 1 0 1 4. That's x transpose, and then I'm going to write my x 1 1 1 1 1 1 -2 -1 0 1 2 4 1 0 1 4. Next up, let's calculate x transpose y, and that would be this thing here, 1 1 1 1 1 -2 -1 0 1 2 4 1 0 1 4 0 0 1 1 3, and that turns out to be 5 7 13. Also we need to invert this. Like I said in last lecture, I posted a link, you can just Google and find a place where you can do all these matrix calculations easily. You don't have to do that if you want to do that. I don't need to see all the calculations, but I do need things written like this, right? So you're calculating x transpose x inverse. Sorry, I need to use a different color for this. X transpose x inverse, that would be 17 divided by 35, 0, -1 over 7, 0, 1 over 10, 0, -1 over 7, 0, 1 over 14. Remember, it's a symmetric matrix. Off diagonal elements, same off diagonal elements, because x transpose x inverse is representing the variance, the coefficients in variance of beta hat. Recall, variance of beta hat is equal to x transpose x inverse sigma square. So this is the when I say variance, what I mean is this is variance covariance matrix, right? It's going to be, so this is the variance of beta naught, coefficient for variance of beta naught. This is the coefficient for variance of beta, variance of beta 1, and this is the coefficient for variance of beta 2 hat, not just not with the hat, right? All right, so let's keep going. So our beta hat is equal to x transpose x inverse x transpose y, which is 4 and 7, 7 and 10, 3 out of 14. If you want to be more precise, it's 0.571, 0.700, 0.214. That's what, at least what my calculation said. Alright, so that finishes our example on page number 32, where you are just fitting a parabola. So now you have the estimate, so your y is 0.571 plus 0.7 x1 plus 0.214 x2 square plus error term. And that's you have fitted the parabola now. Next stop, so on page number 33, it is asking, does this data present sufficient evidence to indicate curvature in the response function? So is there sufficient evidence to say that there is curvature in the response? That is this. So basically it is asking you to test H0 beta 2 equal to 0 versus HA beta 2 not equal to 0 in the linear model y equal to beta naught plus beta 1x plus beta 2x squared plus error term. So the hypothesis testing process is same. Your T is beta 2 hat minus expected value beta 2 hat, which is beta 2, which is under null hypothesis 0, divided by variance of beta 2 hat, which is beta 2 hat divided by sigma square. And then if you go back, this coefficient right here, right, that's the coefficient that should go there. So 1 out of 14. So because it's square root, so sigma 1 over 14, but I don't know sigma, so what do? We replace it with S. What is our S? That is something we have to calculate on side. S square is SSE divided by n minus, this time it's not n minus 2, it is going to be n minus 3 because you have 3 parameters. So n minus 3, that is something to because we estimated 3 parameters. Now what is SSE? SSE is y transpose y minus beta hat x transpose y. Y transpose y is 11 minus beta hat, we just calculated 0.5. I need to write smaller, give me a second. Okay, so my SSE is y transpose y, which is 11 minus beta hat is 0.571, 0.7, 0.214 vector. X transpose y we calculated as 5, 7, 13. So if you simplify it, it's 0.463. So that's my SSE. So my S squared is SSE divided by n minus 3, which is 0.463 divided by n was 1, 2, 3, 4, 5 minus 3, which gives me 232. So my T, getting back to my T, or the test statistic is beta 2 hat, which is 0.214 divided by S times S is 0.232 square root of 1 over 14, which, if my calculation is correct, is 1.67. Now you're going to compare it with, it's a two-tailed test, so you're going to compare it with T alpha by 2 with 2 degrees of freedom, which is 4.303. You can use an app or whatever table, whatever works for your R to find that. So you are comparing this with this. This with this, right? So we fail to reject. It does not fall in the rejection region. It is way. So let's look at it. So this is my T. These are my rejection regions with area 0.025, 0.025. This is the critical value 0.303, and my test statistic is somewhere here 1.67. So it does not fall in rejection region. We fail to reject, so we fail to reject H naught. That is beta 2 equal to 0. Remember, we never say that we do not we accept HA. We either fail to reject or we reject or we fail to reject. That's all. We never say we accept, because even though you have fixed your alpha, you don't know what your beta is. What is the probability of type 2 error? Unless you know that, you don't know about it. Also, if you look at the, so that's one thing. Also, if you look at the width of confidence interval for beta, it is pretty wide. So we can actually calculate confidence interval for beta also, as we've been doing earlier. Nothing has changed, so don't get overwhelmed. It's just that we are operating in matrix world to show you how things work, and actually in real life a software is going to multiply all these matrices for you, but you should know where all this stuff is coming from. So if you look at the try to find the confidence interval. So let's find the confidence interval also. Okay, so confidence interval for beta 2 hat is point estimate. We are talking about large sample confidence intervals, plus minus critical value. It should have come from Z, but because we don't know S sigma, we replaced it with S, so we are taking T 0.025, and because it's a small sample, we're taking T. If it was large sample, this T would, after 30, it would start to look like normal. And minus 3 was 2 times standard error of beta 2 hat. So beta 2 hat is 0.214 plus minus, the critical value is this, standard error is 0.48 times 1 over square root of 1 over 14. It comes out to be 0.214 plus minus 0.552. So this is going to 0.552 is the margin of error. So this is your margin of error, pretty big margin of error, right? So the confidence interval is pretty wide. Wide confidence intervals are never very reliable. The reason is this is just a fake example with very small data set. Another thing that I wanted you to notice here before I stop is, yeah, I think we can stop here. So is one more thing that I wanted to point out. Where is my X transpose X? Oh, never mind. So I'll show it to you later in another example. But basically, remember, that's pretty much it. That's what you're doing. So I am going to stop here.